Hi, everybody. Let's wait for a few more people to join. Okay. All right, so today Michael is going to give a presentation today. Uh, uh, it'll be around midway through class, I think. So Michael, at some you'll you'll be able to tell when it's coming. I think. um, so, before we get to that, I need to wrap up a couple things from last time. Um, Namely, we stated but didn't prove the following theorem. So, theorem, if k delta is an approximate identity.
Can you share your screen?
Thanks. Sorry. Okay. So if actually maybe I'll just include this in the previous lecture because I stated the theorem already. I'll start this lecture with Hilbert spaces. Okay, so we stated this theorem last time. Let's complete the proof. So if k delta is an approximate identity and f is an L1 function, then k delta convolved with f converges to f as delta goes to 0 for every x in the Lebesgue set of f. In particular, since the Lebesgue set since almost every x in Rd is in a Lebesgue set of a given L1 function, this holds for almost every x in Rd. So we have pointwise almost everywhere convergence of the convolution with an approximate identity. So let's do the proof of this theorem. And let me just remind you what an approximate identity is. This is the definition of approximate identity. It's a family of functions indexed by, say, these are real numbers delta with delta thinking positive, so that they integrate to 1. 2 prime is an absolute value. They have this global bound on k. They're less than k deltas. They're less than some constant times delta to the minus d. And then I have the second pointwise down is that they decay like delta over x to d plus 1. This bound you want to use away from the origin. This bound you could use at the origin. It's kind of the way it works. Okay, so let's prove this theorem about approximate identities. And the step, this is going to look quite a lot like the proofs we've done in the past, just with a couple slightly different ingredients in the analysis. So we want to consider such a difference, right, at a point x minus f of x. This in an absolute value is, I'm going to use the first property of approximate identity to rewrite f as f times the integral of k delta. So this is equal to integral over Rd. I'm going to write out the convolution, but then I can subtract f of x inside the integral since k deltas integrate to 1. Dy. And then I can just put the absolute values inside. So the approximate identities are such that putting absolute values inside the integral is okay. Okay, So now we're gonna analyze this uh, this integral, well, by splitting it into the following regions. So this is less than or equal to integral over y less than or equal to delta of the above plus integral over y um, bigger than or equal to delta. And we're going to analyze each of these regions differently. But to do this, we need the following lemma. So pause the proof, and let's prove a lemma. So let's let f be an L1 RD, x in the Lebesgue set of f f. If I let script a of r to be 1 over r to the d integral y less than or equal to r, f of x minus y minus f of x dy for r bigger than 0. So I define this function of r as follows, just integrating, taking the average of this difference over the ball of radius r. Then, as long as I take x in the Lebesgue set, script a of r is continuous. For at all points r bigger than 0. A of r goes to 0 as r goes to 0. And moreover, there exists an m bigger than 0 such that a of r is less than or equal to m. It's uniformly bounded for every r bigger than, strictly bigger than 0. Okay, so these are the three properties we're after for such functions. And then this is going to be the main ingredient in the proof, the proof of the theorem. Okay, so how do we do this? Well, continuity just follows from continuity of the integral, right? So absolute continuity of the integral. This is an L1 function, right? So, well, on a fixed ball of radius 1, say, this is an L1 function. And so then continuity follows from continuity integral. So proof. The integral, absolute continuity of integral. A of r tends to 0 as r goes to 0, since x is in the Lebesgue set. And the measure of the ball radius r 0 is equal to constant times r to the d. So this is just a consequence of x being Lebesgue set. And since it tends to 0, so the above implies that a of r is less than or equal to m for some m for all r in a compact set, right? Because it tends to 0 as r tends to 1, so then it's a continuous function. So it's bounded up to say 1. But then if r is bigger than 1, then the bound is immediate. R to d. We'll just use a triangle inequality. dy less than or equal to, this is 1 over r to the d times the L1 norm of f plus some constant times the absolute value of f of x. And this is finite since x is in the Lebesgue set of f, right? And this is finite L1 and r is bigger than 1. So this gives the bound, a uniform bound. Note that that x is fixed in the Lebesgue set, so it's okay. In this statement, this bound m depends on x, right? So this is m of x, right? X is if for each fixed x, this thing is bounded. So the bound isn't uniform in x. All right, so that proves a lemma, and now we can get back to the proof. So the last step of the proof, we split the integral, this integral into 2 pieces. But actually, I'm going to do more than that. I'm going to chop this outer region into dyadic shells. We're getting back to our harmonic analytic techniques. Let's rewrite this last component. F of x minus y k delta integral over y less than or equal to delta plus the sum from k equals 0 to infinity of integral 2 to the k delta less than or equal to r, sorry, y. Two to the k plus 1 delta of the stuff inside the integral. And I'll call these pieces, this is 1 plus 2. All right, so 1 equals integral y less than or equal to delta y minus f of x k delta y dy. This is less than, or I'm just going to use the bound for k we have near the origin. This is less than or equal to a constant times delta to the minus d, constant over delta to the d. Delta, so I just used the global bound for k using the fact that it's approximate identity. But then this is less than or equal to a constant times a of delta, right? Where script a is the object we had in the lemma. This is exactly a of delta, and this goes to 0 as delta goes to 0 by lemma. All right, so that takes care of 1. Okay, for 2 is broken up into pieces. So each of these, so this 2, on each of these pieces, 2 to the k delta less than or equal to y less than or equal to 2 to the k plus 1 delta. Times absolute k delta y dy. This is, I now use the bound 3 prime for k. So this is constant times delta over 2 to the k delta to the d plus 1, right? Because I have the bound I have for k is that I use this bound, but then on this set where I'm iterating over, I have 1 over y to the d plus 1. well, y is always bigger than or equal to 2 to the k delta. So I'm just going to pull this factor out of the integral by replacing y with 2 to the k delta. So I have 2 to the k delta times d plus 1. So times integral. And I'm free now. I'm going to make this even bigger. I'll integrate over the 2 to the k plus 1 ball. X minus y minus f of y dy. And now this is less than or equal to some constant times 2 to the minus k. I have an extra 2 to the minus k note on the outside times a to the 2 to the k plus 1 times delta. Okay. If you just work out the algebra, that this is what I get from here. So I make 2 to the k plus 1 delta up here, and that gives me an extra 2 to the minus k. Since I have this d plus 1. I have this d plus 1 here. Okay, and I have delta to the minus d, but I have 2 to the k to the d plus 1. So that gives me this extra 2 to the minus k, which is important. So the bound I've proved. So what I've proved is that f convolved with k delta x minus f of x is less than or equal to constant times a the delta plus another constant c prime sum from k equals 0 to infinity 2 to the minus k a2 to the k plus 1 delta. Let me rewrite this last term. So this twiddle means up to a constant. Twiddle is a delta. I'm just going to drop the constants plus. So I have this bound. So next, recall that let me set the file. AR is bounded. So just choose in large so that the sum so for large k, I'm going to want to just use the uniform bound for a. K bigger or equal to n, 2 to the minus k, a to 2 to the k plus 1. Delta is less than or equal to m times the sum from k bigger than or equal to n, 2 to the minus k, which is less than or equal to 2 to the minus n, to a constant, which is, I'll take less than epsilon. So pick epsilon, give me epsilon, I'll fix such an n, capital N. So fix such an n. And then use dilemma to choose delta small enough so that a 2 to the k delta is less than epsilon over n for k equals 0, 1 up to, and there are only finally many such k, so that this is possible. And a corollary to the proof is that f convolved with k delta minus f in L1 also tends to 0 as delta tends to 0. Okay, so that's it. And just note that that L1 convergence is also proved. Okay, Any questions about the argument? This is a bit technical. Let me sync the file. All right, so I just like to present. This is a bit of an abstract theorem, but I want to present a consequence, so an application of the theorem. Fourier series in L1. So I want to prove a general version of a statement that we proved earlier in the class. Okay, so L1 of t is equivalence classes of functions t to c such that it's finite. The L1 norm is finite, and so integrable functions of the torus, and the L1 norm of t is the same object we studied a lot in beginning class, 1 over 2 pi integral from minus pi to pi. We integrate we identify the functions with functions on say minus pi to pi, 1 over pi f of x dx. And then note that this is now the natural, this is the natural class to define. Frozen. To associate to each of such function as Fourier series. So to each f in L1 of t can define f hat of n. It's the nth Fourier coefficient is 1 over 2 pi integral from minus pi to pi. F of y e to the minus I n y dy. So you can define Fourier coefficients, right? Because right, note that these are finite. This integral exists. This is that this is an integrable function, right? And in fact, they're bounded by just by putting absolute values inside the integral, the L1 norm of f. So, okay, so in the Fourier series is, as usual, okay. And at the very beginning of class, we proved uniqueness of Fourier series. So if the Fourier coefficients for a function all vanished, then the function itself had to be equal to 0. So the same theorem holds for in L1, just for functions in L1. So if f is in L1 of the torus, then two statements. One is that f hat n equals 0 for every n, that f of x is equals 0 almost everywhere, right? So f is a 0 function in L1, and 2, that the pointwise almost every Bell sum ability. So the sum from n equals minus infinity to infinity of r to the absolute n f hat and e to the I n x tends to f of x for almost every x as r tends to 1. Sorry, I should write as r tends to 1 for almost every x. So 2 is almost everywhere a Bell summability. And so the proof of this theorem is, first note that 2 implies 1, right? Because if all the Fourier coefficients are 0 and you have pointwise almost everywhere convergence, then you have no choice left but for f to be 0 almost everywhere if these are equal to 0, if the left-hand side is just equal to 0. So 2 implies 1. So proof of 2. Well, we've done this, but the missing ingredient is in this setting where we just assume f is in L1 is the fact that the Poisson kernel is an approximate identity. So the claim is that for every x, this is equal to f PR of x. This is the Poisson kernel. And the proof of claim is apply the dominated convergence theorem. So I'm just going to give a quick sketch of this argument. Apply dominated convergence theorem. And so the ingredient about exchanging limit and integral is done by dominated convergence theorem. And then 2 follows from fact that it's an approximate identity. So you get convergence on the Lebesgue set, and then almost every x is in the Lebesgue set for an L1 function. Approximate identity, and previous theorem. Okay, so that's the application of this last bit of what we did about approximate identities in L1. Now we can the point or a nice application is we can make sense of the Fourier series of an L1 function on the torus. We can make sense of the Fourier series, right? Where we think of a key ingredient of making sense of this object is that we have uniqueness, right? If 2 functions have the same Fourier coefficients, then they're the same function almost everywhere. So they're the same in the sense of being they're in the same equivalence class of in L1. Okay, the next big, so that's one, so this is one application of the theory of building. But we know when we started integration theory that what we were after is understanding Fourier series in L2. So let me just say, we're going to start discussing Hilbert spaces. So maybe or we're going to revisit Hilbert spaces now with integration theory. So the example that we'll start off with is L2 of RD. What is a space? So the L2 norm, so we say f is an L2 of RD if its L2 norm is finite. And we identify, as always, we identify f equals g as L2 functions if they're almost everywhere. Let me write this out better. If f of x equals g of x for almost every x. So two functions are the same in the sense of L2 if they're equal almost everywhere. So what marks L2, what distinguishes L2, and in general, we can define LP of RD. P, say, bigger than 1 via the norm. Where you take the pth power of x. And then if p equals infinity, you just take the soup norm. So this is the range suite of LP norms. L2 is distinguished because it arises from an inner product. So L2 is an inner product space. So you can define the L2 inner product, F paired with G, L2 of RD. This is just integral. We can allow our functions to be complex valued. And then it's just a pairing F by G bar. And then the L2 norm is just given by take F, pair it with itself, take the L2 inner product with itself, and then take 1/2 power. Okay, so it's an inner product space, and it has the following properties. It's a vector space. Two, F times G bar is integrable whenever F and G are in L2. So if you have two functions in L2, then you can take their inner product. Since, why is this true? Integral, this is just a Cauchy-Schwarz inequality.
Could you just remind me, does the Cauchy-Schwarz inequality hold for all inner product spaces? Or is it like
Yes. Yeah, it's a property of an inner. It holds in all inner product spaces. Yeah, I mean, we could prove. So we can prove it, but the proof is basically the same. 3. If G is fixed, you can define a map. F goes to the pairing F with G. You can have for the fixed function. This is linear. It's a linear mapping. And satisfies this property. And then 4, you have the triangle inequality. So Andy, to answer your question, we further answer your question. We could suggest this as an inner product. It's like a bit of a chicken and egg thing. So we want to, I could suggest this inner product, and we want to show that the Cauchy-Schwarz inequality holds for this inner product, right? So this is, I guess I can't just declare this to be an inner product, right? We'd have to we want to show it satisfies some properties, but this is a Cauchy-Schwarz is a property that you want the an inner product to satisfy. So that would be kind of the order of operations. We suggest this is an inner product, show it satisfies the properties of an inner product, one of them being Cauchy-Schwarz. Okay, but I'll relegate, since we've done similar stuff already, I'm going to relegate the proof of this proposition, or of these 4 properties, to reading. So for the proof, see chapter 4 of Stein-Shikharchi. And I want to get a little bit deeper into the structure. So the first property, the first theorem, is that L2 is complete. So the space complete with respect to the L2 metric. This is the metric, and the proof essentially is essentially the same as proof that L1 is complete. So this is not, there's no real essential difference to these proofs. So it follows the same train of ideas. So you can refer back to that proof for the completeness. The next property is called separability. So, and for this, I'm going to hand over the lecture to Michael. Let me just state the theorem that Michael is going to discuss and prove. L2 RD is separable. So I'm going to turn over, I just recording a few notes, and I'm going to note that Michael's presentation is going to cover this proof. Okay, so for separability, I'm going to turn over the lecture to Michael. So I'm going to stop my share. And Michael, are you ready to go?
I should be.
Okay.
I'm trying to get to share my iPad, so it might take a minute.
All right, we see something, but it's all black.
Okay. Is that better?
Yes.
All right. Okay.
There we go.
Yeah. So the theorem I want to prove is that the space L2 of RD is separable. And separable in this case means the following. There are countably many elements of L2. Where their span is dense in the entire space. So by span, I mean the set of finite linear combinations of these elements. Remember, we just said that L2 is a vector space, so we can take linear combinations. And so we want to prove that there's countably many elements where if you take their span, you get a larger set, which is dense in the entire space. Okay, so for the proof, let's first write down what this collection of elements is going to be, and then we can prove its stats. So you might think that we want to use the fact that the rationals are dense in the reals, and we are indeed going to do that. So here is the collection we'll use. Let's call this S. It's going to be a certain type of step function. So we're going to have R times chi sub big R. So R is going to be a complex number whose real and imaginary parts are both rational. And R is going to be a rectangle whose coordinates are rational. So that means like, if you look at like the upper and lower boundaries in each dimension, then those are rational numbers. So note that this is a countable set, which is what we want. And the reason is that if you want to specify an element of this set, well, you have to choose A and B, which are both rational. And then you have to choose 2 times D other rational numbers to determine the rectangle. So we have like a finite number of countable, finite number of rational numbers, which will specify an element. So that's a countable set. Okay, so we need to make a finite number of choices from Q to specify an element of S. Okay. So let's prove that the span of this is dense. So let F be an element of L2. Let's pick some epsilon greater than 0. The first step is to approximate F by a nicer function. So a function which is going to be bounded and has bounded support. So you might have seen this trick before. I think we used it in the proof of dominated convergence. So let's let G sub n, where n is a positive integer, be F, or sorry, I should put x's. G sub n of x equals f of x if both x is small magnitude and f of x is small magnitude. Otherwise 0. So we're just sort of like putting f at a ball centered at the origin and also keeping it small in magnitude itself. So what do we know? So G of n should converge to f exactly at the points where f is finite. And because f is in L2, that means that f should be finite almost everywhere. So that means that Gn converges to f almost everywhere. Okay, furthermore, let's take a look at this function f minus Gn absolute value squared. This is sort of a silly function because it's always either 0 or f, or absolute value f squared. So we have that this is bounded. And the reason I'm saying this is because we're going to use dominated convergence to prove something about how G goes to f, or sorry, Gn goes to f. Okay, so by dominated convergence theorem, this means that the integral of f minus Gn squared goes to 0 as n goes to infinity. Because this function is uniformly is bounded above by an integral function, namely the value of f squared, and it goes to 0 almost everywhere. Okay, so here we go. Okay, so in particular, if we take a square root, then we get that the L2 norm of f minus Gn goes to 0. So we use the dominated convergence theorem on the specific function to prove a statement about the L2 norm. Okay, so let's say, so now that we've proved that this goes to 0, we can like let G be Gn, where we choose n large enough. And let's give ourselves some rooms. Let's say f minus g big N in L2 norm is less than f1 over 3. Okay, so we've approximated f by a function g, which is bounded and has a bounded support. So in particular, that means f is in L1. G is in L1. G itself is integrable. So if you recall a theorem from chapter 2, that means that we can approximate G by step functions, which is going to tie in with our definition of our S, because we want to look at step functions. Let's say phi is a step function. Where close to G in L1 norm. Specifically, I'm going to use this like magic value, which is going to help out at the end. Epsilon squared over 18n. That's going to cancel out and give us the answer we want. Okay, we can also choose this phi so that, remember that G is bounded above by a capital N. We can also assume that this holds for phi. The reason is that if it wasn't, then we can like just sort of project it onto the of the ball radius. If not, I don't know how to say this. Let me see. Sort of clip phi at absolute value equals n. So like if absolute value of phi is 2n, then you can divide it by 2, and you're still, that only makes it closer to G at each point. Okay. So what do we know? We know that G and phi are both bounded by n, and we know that they're close in L1 norm. So, and we want to prove something about how close they are in L2 norm. Well, we can do it like this. So the difference between them in L2 norm, by definition, this is just the integral of G minus phi squared to the 1/2. Maybe I should zoom out a bit. And we can take one copy of absolute value G minus phi and replace it by 2n, because they're both bounded by n. So 2n absolute value of G minus phi to the 1/2. And now you can see that after we pull out the 2n, we'll have the L1 norm. So this is 2n times the L1 norm of G minus phi, all to the 1/2. And now you can see how this is going to work. So we have 2n times our bound that we wrote down above. And if we write down all the algebra and we cancel, we get exactly epsilon over 3. So that's why that value is chosen. Right, so the key idea here is that the bound on the L1 norm gives a corresponding bound on the L2 norm, given that both the functions here are bounded. Any questions so far? I think there's just one more step. All right, let's finish up then. So we've bounded our original function f by a function which is bounded of bounded support, and then we bounded it by a step function. Now we have to round off the step function so we get something with all the rational parts. So let psi be an S, where also psi is bounded above by n, and let's say the difference L1 norm between phi and psi is at most well, the same value. So the way you do this is you take phi, our step function. Let's say you write it in canonical form, and then you take all the coefficients and all the rectangles, and you sort of approximate them by rationals. And you can do this as close as you want. In particular, you can get this value again. Okay, so, and then we do the exact same thing, right? So we have the same L2 bounding. Oh, sorry, this is an L1 norm. But this is an L2 norm, and we get the exact same result by doing the exact same inequality. So we also get an epsilon over 3 between the two L2 norms. Okay, so now we're basically done because we have f minus phi in L2 norm being less than f minus g, g minus phi. This is by the triangle inequality, and phi minus psi. And we have 3 epsilons over 3. So we just get our final bound. So we prove that there's an element of, I'm sorry, E is in span of S.
Yeah.
Because what we're doing, we're taking each component of E and like rounding it off. So we get like a sum of elements of S. So we get something in the span of our original set, which is close in it to, so we're done.
Very nice. So there's already a question in the chat, and Andy asked if L1 is separable. What do you think, Michael?
I didn't think about this beforehand. I feel like the answer is probably yes. I think we can do a similar thing with, you can take a step function which is close in L1 norm. We use that fact in this proof, and then we can round it off again. The proof is probably easier than this one, actually.
Yeah, excellent, right? Yeah, you had to maneuver a little bit to use your approximation theory in L1 to get approximations in L2. So it looks like the same, like an easier version of this proof should work, right? Mm-hmm. All right, so then bouncing off of that, what do you think about LP for any P between 1 and strictly between 1 and infinity?
Well, I would just try to replace 2 with P in this proof and see what happens.
Yeah, I think that sounds.
I think that works.
Yeah. So there's one catch is if P is less than, so that should work for P bigger than. Oh no, so okay, sorry. So P is always bigger than 1. Yeah, you're good. Okay, yeah. So that's good. So so these are all separable. So L2 is a separable. It's a inner product space, and we'll see. It's called a Hilbert space, which we've seen already a little bit. Pre-Hilbert spaces, we didn't have completeness before, or we didn't see Hilbert spaces because the little L2 was a Hilbert space, which we had before. And then these spaces L1, LP for P not equal to 2. These are typically called Banach spaces, which are just normed linear spaces, separable normed linear spaces. So the Banach space is not a Hilbert space with that because it doesn't have an inner product structure. So this is the typical word. You might see this word might come up, but all it means is the examples you should have in mind are LP for P not equal to 2.
Don't you also need completeness for it to be a Banach space?
Yes. So completeness too. So completeness with respect to the metric, and the same proof that we just didn't do for L2 that we did for L1 basically works for all these LP spaces as well. So these are called, I guess, so the LP spaces are often called Lebesgue spaces, I guess, and these are all complete with respect to their norm and separable, and therefore they're linear spaces, and so they're called Banach. They fall into the category of Banach spaces. But yeah, so completeness too. But the proof is sort of is essentially the same of completeness for all these objects.
Yeah, Joseph's question.
Yeah.
Yeah, so for arbitrary p, I think if you just look over this proof, whoa, okay, let me stop moving on me. Okay, I think if you just, so if you replace 2 with p in this proof, so you have an LP function, our first step was to look at this function of absolute f minus gn to the power p, well, to the power 2. So I think if you replace the 2 with a p, then you can prove that you can approximate f with gn in LP norm. And now, now everything else sort of takes place in L1. So I think, yeah, I think it shouldn't be too hard to generalize this.
So would you also have to change your bound epsilon squared over 18n based on whatever?
Oh yeah, probably.
Is that correct?
I think you need epsilon to the p over something in terms of n.
Maybe
you might need like n to the p minus 1 to cancel everything you're getting rid of. Yeah.
Yeah, p minus 1 probably, right? Epsilon.
Yeah. Good point.
Thanks.
Yeah, exactly. But the concept is still the same. You need to finagle a little bit to get these to get the constants right. But I think that the idea for the proof should work just for any p. Okay, thanks, Michael. This was excellent. Any other questions for Michael?
If nothing else, I actually had a question.
Yeah.
So I've heard of separability before, and it's not quite the same as how it's given here, because usually if you just have a topological space, then you want just any countable set of elements to be dense. Not their span, just the set themselves.
Not the span, but just the set. Okay, so I guess this is like vector space separability, right?
Okay.
So taking linear combinations of things, like topological spaces aren't linear spaces, right? So you can't take linear combinations. So this is, I think this is probably just the way to state things for a vector space, right?
Okay.
Does that make sense?
Yeah.
Michael Wren.
Yeah, I think that makes sense too. So you might notice that in the proof that we just did, you only take like rational combinations of things in S.
Yeah.
So you might actually end up getting just a completely countable set if you take the rational span.
If you take an arbitrary, sorry. So I want to see the same in this vector space notation. So an arbitrary countable set. Is an arbitrary countable set dense? Is this the question?
Is some countable set dense?
Okay. Yes.
Yeah, I think what we proved is like if you can actually just take the rational linear combinations of S.
Yeah.
So countable.
Yeah.
So that's fair. Although I don't know, maybe that might not be the same for arbitrary vector spaces.
It's probably the same, I think. Thanks, Michael Wren, for the comment. Okay, any other questions?
One very quick question on the definition of Banach space. I thought we can drop the criteria of separability.
Yeah, so separability. Okay, so separability is often included with a definition of a Hilbert space. Okay, so LPs are separable bonds. So it's a matter of terminology whether it includes separable or not. But you're right. I think for Banach space, same for Hilbert space. It's a matter of convention whether you say include separability in the definition or not. For Hilbert spaces, the separability comes in because we want to we'll want to find orthonormal bases for a Hilbert space. So the separability will allow us to prove a theorem, which I'll state in a minute, that we can find an orthonormal basis. So yeah, so maybe if we leave out separability for Banach spaces, maybe we could just say that the LP spaces are separable Banach spaces, rather than include the definition. Yeah, sorry, it's definitions. Yeah, there's often it's a matter of taste how you define things. Sometimes, especially in analysis. But yeah, that's a good point, Samuel. So separability is often included in a definition of Hilbert space, specifically because we're going to use it for something important. Okay, so if there are no more, any other questions for Michael? So sorry. If not, maybe I'll take the screen. Can you
Yes.
pass me the screen back?
There.
Okay. And thanks, Michael. That was excellent. Okay, so we just proved that L2 is separable, and so we've been discussing Hilbert spaces, but let me just remind you guys of the definition. So H is a Hilbert space if H is a vector space. Let me write this out. Inner product such that is linear. GF, and the inner product of F with itself is greater than or equal to 0. H, then the norm is just inner product of F with itself. So Hilbert spaces are norm spaces. 3, the norm of F, I should keep on writing L2. Oops. Equals 0 if and only if F is equal to 0. For L2, this is not a problem because we're saying the functions are identified if they're equal almost everywhere. So this is true for L2. Cauchy-Schwarz inequality and triangle equality hold. Five, H is complete with respect to the metric. So it's complete as a metric space with respect to metric. Just take norm of F minus G. And then the last part, separability. So for Hilbert spaces, we're so again a matter of convention, but we're including separability in the definition. So H is separable. So meaning we have a countable dense subset. Okay. Okay. So examples that we've seen. So now are Hilbert spaces. We already saw little L2 of Z. And then, just CD with the usual inner product, dot product. This one is finite dimensional. Okay. Okay, and already when studying little L2 and L2 of the torus, we saw the concept of orthogonality. Switching between capitals and not. Namely, we say, so if F and G are in a Hilbert space H, are orthogonal, if the inner product between F and G is equal to 0. And then the notation for this is analogous to perpendicular vectors. So we write an analogy for the geometric interpretation in CD. We write F is perpendicular to G. And then we saw before the same exact proof. If F is perpendicular to G, then the norm of F plus G squared is equal to F squared plus G squared. So this is something we saw before. And then a family or a function of elements is called orthonormal if is equal to if I take inner product between two elements of the family, a family, let's call this EK, either finite or infinite, is equal to 1 if K is equal to L, and 0 if K not equal to L. So they're pairwise perpendicular to each other, and they have unit length. And then proposition, which immediately follows from the previous observation. If I have K equals 1 to infinity orthonormal, and F is equal to AK EK for some finite sum, then some linear combination of these, then F squared is equal to the sums squared of the AKs. And this is just the Pythagorean theorem. So this is the Pythagorean decomposition for orthogonal. This is the Pythagorean theorem for perpendicular elements. And this is just a simple consequence, applying it repeatedly. Okay. So we next get to the notion of a basis. So definition, is an orthonormal basis of H if these are orthonormal, and the span of the EKs is dense, i.e., if finite linear comms linear combinations are dense. Okay. All right, so this is the notion of orthonormal basis. And the main theorem about Fourier series in L2 that we stated but we weren't quite able to prove completely because of the failure of completeness for the L2 of the Riemann integrable functions will be an easy consequence of the following general theorem about Hilbert spaces, about bases in Hilbert spaces. So we have the following theorem. The following are equivalent. So if any one of these assertions hold, then the others hold as well. So I finite so an orthonormal so the propositions about orthonormal families. So take an orthonormal family, the following is scope: find linear combinations of elements of UK are dense. So that's property 1, property 2i. If F is an element of H, and if I pair F with any element of the family and get 0, then F equals 0 for every j. If this is true, then F equals 0. 3, if F is in the Hilbert space and Sn F is defined to be F paired with EJ 1 to n, then SNF tends to F in norm, which means that this just means that SNF minus F in the norm goes to 0. It goes to infinity. And the last equivalent proposition is if I if I take F, then the norm of F squared is equal to the sum from k equals 1 to infinity of taking inner product of F with EK and squaring these. Okay, so each of these properties are equivalent. And what do I want to say? Maybe I wanted to say something else. Right after this. Sorry. No, okay, so what I wanted to say is that this is an abstract statement about Hilbert spaces, but as a corollary to the statement is the following theorem about Fourier series. So if F is an L2 of the torus, then a Parseval's identity holds. T squared is equal to the sum from n equals minus infinity n squared. B, f goes to is, so if I take f and associate to it its family of Fourier coefficients, this is an isomorphism of Hilbert spaces. L2 of t to little l2 of z. And C, the partial sums, Fourier sums of f, converge to f in L2. So this will, this theorem that we prove for Riemann integral functions extends to the full space L2 of the torus, and in particular this mapping where we take f and associate to it its Fourier coefficients. This is an isomorphism of Hilbert spaces. So what does isomorphism mean? The Hilbert space structure is preserved as a map between Hilbert spaces, and moreover that the norm is preserved. So right, that's Parseval's inequality. So the norm of f is equal to the norm, the little L2 norm of the sequence of Fourier coefficients. Okay. So so we'll do this. We'll formally write down the proof of this corollary, but you see you can see the elements here. The key ingredient, the ingredient, or what's behind this is that EK is an orthonormal basis. Okay, so meaning once we have any of these conditions for the EK and the little L2 of G, then the rest hold. In particular, you have pointwise convergence, and this is Parseval's inequality here. Because remember the Fourier coefficients is equal to f paired with EK, where EK sorry, this should be K. All right. So any questions about, actually, I think I'm out of time. So in the next class, we'll start by proving this theorem, this for equivalent properties of an orthonormal, and then we'll quickly deduce after that this corollary. And then I think the next thing we'll get to is the Fourier transform. So the continuous version of the Fourier series. We'll start that on Thursday. So any questions at the very end here?
Another very quick question for the definition of span. I wonder why do we kind of loosen the condition, saying that span ek is length in h instead of saying span of ek equals to h.
Why we can't get equality. So it's just this infinite dimensional versus finite. So it's that. So you want a basis, the span of the basis to be equal to the space in the case of a space of finite dimensions, and it just turns out that it's just not quite true. Well, what you have is that what you have is something like this. For if you take any arbitrary f, and you it's you have this fact. So you could say that f is equal to this infinite linear combination, right? So what does this mean? Right, that means it's suggesting you should be able to write in which case you'd have f to be equal to an infinite linear combination of these things, of the basis elements. But this equality is the symbol that you want to be precise about. So does that make sense? So equality holds in this sense, right? And that these, if I take a finite collection of the basis linear combinations of basis elements, I can get as close as I want to f. But since this doesn't hold necessarily in a pointwise sense, I think this is why you refrain, I think, from saying that all the functions are equal to and possibly infinite linear combination of basis elements. Does that make sense? It's just a matter of semantics, in that I think you want to remember that this is the best you can. This is what you mean by this equality. Is that?
So as far as I know, that span ek refers to finite linear combination instead of infinite linear combination.
Yes. The collection of all finite. The collection of all finite linear combinations of this infinite of this selected from this infinite family of functions or of elements.
I can't see what you mean now, because I thought that can be infinite linear combination.
So span typically refers to finite linear combinations of even but sampling from a possibly infinite family of objects.
I see. Thanks a lot.
Okay, guys, I need to jump off to a seminar, so we can get to more questions if needed on Thursday.
Thanks.
Thanks, guys. Thanks for the presentation. Bye-bye.
Thank you.
Bye.